Okay, so Cora's already done a great job of introducing Sam in his talk, but that's what we're getting now is more on these gradient flows. So,
okay. Thank you. Yeah, so thanks to the organizers for letting me speak and for letting me speak today, and for putting about 3 or 4 speakers earlier today who have included stuff that I'm vaguely going to talk about, but they've made my life easier in that way. So I'm going to talk today about a couple of projects I've done with some people at Warwick. They're sort of all algorithmic in character, all about sort of solving statistical problems using a class of algorithms known as gradient flows. And we'll sort of unpack what that is over the next 20 minutes or so. Yeah, it's the end of the week and it's been a very busy week, so I'm trying to say as little as possible, as clearly as possible. So please help me with that. Okay, so the main things I'm saying today are hopefully pretty uncontroversial. They're certainly not intended to be. So the first one is that, we find in practice that many statistical tasks that we care about, at some stage, what happens is you sit down at a computer and you solve an optimization problem, okay? And so a lot of different ways for solving these problems have what I would call a gradient structure in a fairly, as you would expect, kind of way, and we'll see examples. And at some level of abstraction, finding the commonalities between these different methods is useful. As someone who does a bit of theory in my own life, that's useful for analysis, but it's also useful for synthesis and coming up with new algorithms that let us sort of make progress into problems that would otherwise be a bit difficult to address directly. And sort of the reason I think of it as being pertinent to this workshop is that there's been a rich sort of collection of motivating applications from PostBase, because to some extent, what is often happening in PostBase is, you say, I want to do something a bit like Bayesian inference, but I have some other priorities. And encoding priorities in an optimization problem is a very natural thing to do. You sort of know where things need to go to some extent. So we've sort of seen examples, and I'll point to them here and there, but I sort of expect there to be even more over time. So this is why I sort of want to flag it. So this is all work with people in Warwick. So on the far right there is Adam Johansson, who's a professor in sort of computational statistics. Second from the right is Juan Kuntz, who was his postdoc for some years and is now in industry, but really was very instrumental in starting these projects and pushing them along. And then on the left are the PhD students who've done the heavy lifting. So Rocco Caprio and Jenning Lim, both are really terrific. I've worked most closely with Rocco, but they both have great work ethic and they're doing great work. So I can't speak highly enough of them. Okay, I put this in every talk, and particularly when I'm seeing an audience with people I don't necessarily know, it applies double somehow. I think it's not useful for you to see a stranger confuse you for 20 minutes. So definitely stop me if we're sort of veering off track. Okay, so as I said, when we're doing statistical inference, often it boils down to a question of statistical computing, whether it's optimization, sampling, or something else. But at some level of abstraction, you will often end up with an optimization problem. Okay, this is sort of the big picture. And so I'm going to take a broad view of optimization today, which is that it can mean many things in terms of what are the variables we're optimizing over. Okay, and so I think the version of optimization everyone thinks of first is what I would call parametric optimization. You have some sort of finite dimensional object that you are optimizing, and for today it'll live in a Euclidean space. But we'll see examples of all this stuff on the next slides. One thing that's been a sort of fruitful perspective, particularly in recent years, is to think about different tasks involving stochastic processes as being an optimization problem over a space of probability measures. Right? So you have some sort of space X of latent variables or parameters, and you want to sample those. And so when I write P of X, that's just probability distributions on this space, and that's what we're optimizing. We're sort of manifesting a probability distribution in some algorithmic way and letting it solve a problem for us. And then the third thing I'll talk about, which is sort of what the focus of our work has been what I would call hybrid space problems, where you're doing both of these things at the same time. Okay, and I'll try to convince you that this is not just an edge case, but actually something you will see cropping up again and again after you recognize it's a type of problem. Okay, so let's give examples. So the last few times I've given this talk, it's been to an audience of people doing stochastic control, machine learning, and information theory. So I have to warm them up a little bit, but hopefully everyone here is familiar with maximum likelihood estimation in some capacity, even if to slag it off. So maximum likelihood estimation is we write down a parametric model for our data, and then we maximize that function, as a function of this parameter. And you can do various variations on this. Maybe you add a penalty term to do some regularization and you do penalized MLE, or you use something that's not technically a likelihood, but you're prepared to pretend it is, and that's what M estimation is, more or less. So that's sort of the classical statistical example. Sort of another one, which is relatively familiar to a Bayesian audience, but keenly familiar to a computational stats audience, is this task of variational approximation, where someone hands you a probability measure pi, which is not particularly tractable, and they'd like to answer questions about it. And so instead of going through a very difficult process of sampling from it, which we will get to, you sort of say, I'm going to cut my losses, and I'll take some parametric distribution and make the best approximation I can within that world. Right. So here it's I say I'd like to fit a nice Gaussian to my distribution, so I have some parameters which are the mean and covariance of that Gaussian, and I will minimize this divergence function to get the best fit, at least measured in this way. Okay. Now, moving into optimization over measure spaces, my entry point for this was sampling, because that is what I do with a lot of my time. Right? Someone hands me an unnormalized probability distribution and says, I'd like some nice samples from this distribution, please. Now, you can formulate this task in 1,000 different ways, because there's so many different ways of measuring distances on probability space. And so you can write down whatever divergence you like and say, I will minimize the divergence between my decision measure mu that I'm sort of evolving, if you like, and my target measure pi. And my experience with this is that if you choose almost any other function other than the KL, you will run into trouble algorithmically at some stage. There are not really generic formulations for how to do this which work nearly as well. I'm happy to be proven wrong, but I haven't been yet. And so if you agree that the way you're going to solve the sampling problem is to say, I'm minimizing this relative entropy term, there's a nice reformulation of it in terms of this energy entropy decomposition, as a physicist would call it, which is to say, okay, if V is the negative log posterior density, let's say, what I want to do is spread out a measure over space so that I spend time where posterior density is high, but I have a bit of entropy that disperses things for me. Okay, and you can sort of a 2-minute calculation tops to show that you have the same solution here. But this nice decomposition is quite useful algorithmically, because somehow you have the smooth part of the objective, which is this expectation, and the sort of slightly troublesome entropy that we will sort of see showing up later. Now, another thing you can do, which is maybe a little bit more exotic, but has gotten a bit of attention in recent years, has been doing variational approximation in what I would call the non-parametric mean field setting. So you're saying, I'm not prepared to approximate this distribution with something parametric. I think that's sort of too impoverished in terms of what it can represent. I'll approximate it with a product measure, but I'll let each of the terms in that product be as flexible as I like somehow, right? And so again, if you set this up as a KL minimization problem, you get this nice decoupling of the loss function, and this is something you can solve with particle methods. So this is something that some people at Columbia operations research have done in the past year, amongst others. And it's sort of interesting in the context of things like non-conjugate models, basically, where sort of basic coordinate descent variational inference wouldn't make sense. There's various other sort of metrics you could throw in here, things like integral probability metrics, stuff involving kernels, stuff involving other information theoretic divergences. The next talk will involve some of these, so I'll leave it there. But these are some sort of entry-level problems here. And now hybrid spaces. So I've condensed this a bit to how I would speak about it in other talks, but with a statistical audience, we can get away with it to some extent. So one starting example here would be fitting latent variable models to data, right? You have some parameters theta, they give rise to some unobserved variables x, and then you see some y that depends on that x. So you have a sort of separation there. Now, this is something where in principle, on paper, you can say, yeah, I'm just going to do maximum likelihood again. That's a well-posed problem, and I'm allowed to do that. But once you start trying to implement that in practice, you will see that I don't know what the likelihood is. I don't know what the gradient of the log likelihood is. And so if you turn that into, you write down gradient descent for that model, that's not something you will be able to do directly. Okay. And so what people often do in these models is sort of a coupled problem where you say, okay, what I'm going to do, if I could observe these latent x's directly, then maximum likelihood would be fine. Right? So if I can impute what I haven't seen, my problem becomes easy again. And so what I will sort of alternate doing is I will say, given my current estimate of the parameter, I'm going to impute what I haven't seen, and then use that to improve my estimate of the parameter. And I sort of repeat these several times, right? And this is what is known as the expectation maximization algorithm. So hopefully many people will have seen that. So this is sort of, the entry-level version of a coupled problem, because you are solving an optimization problem for these parameters theta, but you're implicitly solving a measure value problem when you're imputing these x's, okay? And I guess, I've been a bit vague here with latent variable models, but of course there'd be things like, mixture models are a sort of standard example, hidden Markov models are another favorite, and there's sort of various ways you can enrich them from there. Another example would be what I would call unnormalized models, and some would call energy-based models. So these are models where you sort of specify something parametrically, but you're sort of somehow a little bit lazy about it. And you say, I specify that the density of this parameter is proportional to this function. And there's some normalizing constant, but you say that's not my problem. The normalizing constant is whatever it needs to be for things to integrate to one. But if you ask me what it is, I actually can't tell you somehow. Okay, and so in this setting, you run into the same problem where you can say, yes, I'm going to do maximum likelihood. And then you start writing down the likelihood and its gradients, and you still don't have them. And there's a similar problem here where essentially, one way of getting your hands on this gradient is by solving a sampling problem. Okay, and it's a nice calculation to do at least once in your life. And so this is related to what Jeff Hinton developed as contrastive divergence, originally for sort of Boltzmann machine type stuff, and also to Monte Carlo maximum likelihood, which Charlie Geyer had worked on in the 90s. But there's various forms of the same idea. Another example which I find very interesting, which has sort of been done to some extent, but not really from the perspective that I have in mind, is doing distributed Bayesian inference. Okay, so you can imagine if I'm doing distributed Bayes and I don't want to be sending actual data between machines, what I could sort of ideally do is sample from the local posterior on each machine, which is what you would imagine, let's say, and then sort of send parametric messages between machines that try to drive the different posteriors to consensus. Okay, you somehow say, okay, what's missing from this machine? It's this kind of a function, and I reweight over here. So there's ways of formulating this as a nice optimization problem. It's quite close to what people do in expectation propagation, if people are familiar with that. But essentially what's happening is you are actually solving several sampling problems, one on each machine, but then also solving an optimization problem for how should I tilt what's happening on each machine with a Gaussian kernel or something like this. I can discuss that with people offline if they're interested. And so yeah, the opinion I would like to bring here, and it's not really just to do with the fact that we worked on it, but my experience is actually problems like this are more prevalent than you would expect. Once you start seriously thinking, if I'm solving this problem as a full pipeline and I'm honest about all the hyperparameters that are involved in the different parts of the problem I want to solve, you will see that you have sampling problems and optimization problems coupled to one another in interesting ways. Okay, so I think it's something that's worth looking at. I don't know if I have it on the slides, but there's a very nice chapter in the upcoming Handbook of MCMC by Alex Bouchard-Cote and these people at UBC on MCMC-driven learning. And they're really describing a lot of problems that have this same structure, where you're using MCMC coupled to another example. Actually, yeah. So having spoken to Alex about this in the past, one other good example of this is computing Bayes estimators. Okay, you're sampling the posterior distribution and you're solving the optimization problem that defines the Bayes estimator. So of course, we sort of get used to the idea that the Bayes estimator is closed form because it's just the posterior mean or whatever. But in plenty of examples, you can have something more complicated going on. Okay, so how do we do optimization? Well, for generic optimization, what we like to do is some form of local search, right? We sort of say, okay, instead of being very clever and trying to solve the problem in one hit, what I'm going to do is take an approximate solution and improve it and improve it and improve it. And because we have very fast computers, that's sort of a sensible thing to do. Now, if you want to conceptualize local search, you need some notion of locality. And so what tends to be the case is we do optimization in metric spaces. And so the way we come up with local search algorithms is we specify a metric, and then we sort of make that a bit more concrete, let's say. So when I talk about metrics here, I'm really not talking about anything very fancy. In each instance, it will be the thing you would think of first. When I'm talking about parametric optimization, think of us as working with the Euclidean metric on the space. For measure valued optimization, I would put a sort of transport metric on the space, much like Paco was doing. And for hybrid optimization, we just sort of put them both together in a way that you might expect. Okay, so once we specify these, then we can say, okay, if I want to solve any of these optimization problems, I will do local search with respect to this metric. So conceptually, what is the optimization problem? Right, we start by writing down our objective, and we say what we're going to do is we're going to start with some initial guess and gradually push it towards something better through what's called a proximal point method, where essentially you say, right, I'd like to stay close to my initial x naught, so I put in this quadratic penalty, but I'd also like to make f smaller. Okay, and so usually you can't implement these steps exactly, but if you take h nice and small, this problem becomes convex and well-behaved, and you can solve it in practice. Okay. And then if you can conceptualize sending this step size h to 0 and putting things into continuous time, this becomes what people would call a gradient flow. So here, sometimes the gradient will be the literal gradient, as you know and love. Sometimes it's sort of a conceptual gradient that means something different in a context. But this is what people mean by gradient flows, or it's one presentation of it. So this is the way I think of it. If you're solving these elaborate problems or simple problems, what can you do? You specify a metric structure, you receive an optimization algorithm. Okay? If you specify the structure well, you will receive a fast algorithm. If you specify a bad structure, then good luck to you. So let me just quickly say what these look like in practice. So on parameter spaces, you have your minimization problem. It's conventional. The gradient flow is an honest to God ODE, as you would expect. When you discretize this in time, you get the gradient method or gradient descent. Now, if we move to optimizing functions on measure spaces, and here I sort of break up the objective as this smooth thing F plus this entropy term, which is sort of ever present, right? Now your evolution becomes a partial differential equation for mu2, what Tucker was calling the continuity equation. Okay, and so formally, it's another gradient method. You're just flowing things downhill. Now, in practice, because I'm interested in problems of high dimension, I'm not interested in solving PDEs as PDEs. I'm interested in turning them into particle methods, basically. So I discretize in space. So I get a bunch of particles xt, and I get a system of stochastic differential equations in this case. And so in practice, this is what people would call the mean field Langevin Monte Carlo method. Okay? So people are used to it in the case where you only need one particle for the sort of standard sampling problem. But when you have more advanced objectives, you need more. Okay, and so finally, with Rocco, Jennings, Juan, and Adam, we've been interested in these hybrid spaces. So again, what happens? You have this joint objective that involves this parameter theta and the measure mu. And then your formal gradient flow is this hybrid ODE PDE. The parameters are evolving, the measure is evolving. And as I said before, you want to turn that PDE into something you can simulate well in high dimension. You move to particles, and you get these sort of coupled things here. And so this space-time discretized method is what we call particle gradient descent. And that was sort of the first paper on this topic. Okay, just a quick word on theory. So in each case, I think this is worth explaining. So for sort of convex problems, as you might understand them typically, the theory for each of these methods is very strong. We understand them as well as we understand any algorithm, pretty much. What's also nice is that in each case, there's some sort of robust notion of convexity that is more forgiving, right? We sort of know, particularly in Bayesian statistics, the problems we're solving are not all convex, right? But we sort of know that they can be solved in many cases anyways. And so we have a nice mathematical language for talking about these. So I would say this sort of robust solution theory is quite well developed for parametric optimization with what people would call Polyak-Boyasevich inequalities, this sort of thing. For sampling, they're even better developed, right? With things like log-Sobolev inequalities and these sorts of things, because people in sampling have always been interested in non-convex problems, partially because these sampling problems came from physics. Right? And for hybrid spaces, it's one thing we haven't fully developed yet. Actually, it's sort of, we know the rubric we might want to follow, but there's some interesting questions that are quite open there. Okay, so I'll wrap that. So as I said, optimization problems are very widespread in statistics, but I think it's worth keeping in mind that they might take a form different than what you're used to. It's not all, regression problems, let's say. Yeah, it's often possible to solve problems like this with some notion of gradient descent. And something I haven't really had time to talk about is, we can even systematically improve on gradient descent. So optimization people here will know that, for parametric optimization, you would often rather use something like an accelerated or momentum method. That's something we know how to develop systematically on these other spaces as well. Okay. Yeah, and finally, so identifying these commonalities is useful for sort of synthesizing new algorithms, existing algorithms being analyzed, and tackling new problems. And there's lots of open problems I'm very happy to talk about. I'll stop there. Thank you very much.
We have time for questions. Anyways, all right. So it's really cool to think about these hybrid problems, and the first thing that popped into my mind is actually variation autoencoders. Because every time people study them, they are kind of immediate. I mean, it's in the name, right? You are positing a variational family immediately. But in principle, I imagine there's nothing stopping you really from solving it over the space of all measures. Yeah, I mean, obviously, it's never going to be convex, particularly in theta. But is that something you thought about? Is there any actionable algorithm coming out of this that you could possibly transfer to people that want to work on VAs?
Yeah. So fortunately, yes. On the paper before I joined the project, this was sort of one of the things they were doing with what you would consider a sort of shockingly low number of particles, given the latent spaces involved and so on. But they could really get something useful out of it. Yeah.
What was the small number of particles?
Well, 10. Yeah. I don't know the details of the experiment, but it was certainly, not what you would expect from most theoretical results.
Any other questions from the audience? In that case, oh, sorry, madam, yes.
Well, no,
Okay.
the next.
No,
Yeah,
sure.
please.
Okay, so deep learning people love automatic differentiation.
Yep.
Right, so John basically mentioned this leading example, right? So I'm just wondering in practice, like all of this framework about, let's say, combining parametric and non-parametric, like how do you implement these things in a sort of like a deep learning friendly way?
Yeah. So it certainly is all AD friendly and even sort of nicely parallelizable in most cases, because what is typically happening is your theta is, classical optimization, nothing fancy going on there. And then you have a collection of particles representing this measure that you're evolving. And they are also generally following some gradient. And so through sort of AD pipelines, that will be perfectly well behaved. And yeah, because we're interested in using particle methods, maybe not with a huge number of particles, but at least a moderate amount, putting them on a GPU to sort of evolve in parallel as much as possible is also something we try to do. But it fits.
Let's thank Sam one more time.